So what I'm showing you here is a do-it-yourself under $40 UVC germicidal lamp sensor. This light is about to go on. There you go. The visible blue light is not the UVC germicidal wavelength, but rather 2% of the energy goes into some visible light. Notice that the sensor came alive. It is measuring the 254 nanometer wavelength energy that's falling on it. The reading on the voltmeter is increasing during the first couple minutes. As the lamp heats up, the output from the light will increase, and then it'll become constant after that. The sensor shown here is under $31 or about $31, and the voltmeter you're looking at is a very cheap one. It's only $5. So under $40, and if you have some soldering skills, anyone could do this. Here is the sensor we're dealing with. It's available from a South Korean company that makes a range of similar sensors for UV applications. The device is 3 terminals, very simple, all of the electronics built in, supply 5 volts and a voltmeter, and one is in a position to measure UV output from any lamp. Here's the responsivity, peaked at 254 nanometers. And the range you see there is the entire UVC range. Responsivity of the device is shown here. Take the voltage, divide by 0.355, and the numeric answer is the milliwatts per square centimeter of flux falling on a sensor. So before we begin assembling this, I want to show you all of the parts that represent this very low-cost UVC sensor that most anyone can put together and use. All you need to do is have some moderate skills of soldering and connecting things. You'll see that in a moment, how simple this is. Over here is the UVC sensor. It is the most expensive part. It's $18. It is tuned only to be sensitive, responsive, that is, to the UVC light at 254 nanometers. It will now respond to any energy outside that wavelength. So visible light will have no effect upon it. The 5-volt charger here from Amazon costs only $8. The power jack you see here is $1, and the board to which we're going to mount these components is $4.25. That represents about $31 of the cost. Now you're going to need a voltmeter, and the cheapest one that I could find, and one which is more than adequate for this application, is shown here. You can find this on the web. Believe it or not, this thing is available for only $5. If you already have a voltmeter, then you're good to go. Now, I've begun to put components on this board, and I want to show you exactly what I did and why I did it. But first, let me describe this board as holes on a 0.1-inch grid, fairly standard grid arrangement for PC boards like this. Each hole is plated through, but the holes are isolated from each other. So being plated through, they'll allow me to solder the components onto the board and then add wires to connect them in the appropriate manner. Now what I'm trying to show you here is this can, transistor can, in which the photodiode is contained, has a little tab, and you could see that on the opposite side of my thumb. That tab now allows us to identify which terminals are which. When we turn this over, one will find that the, let's see if you can see that this terminal is the 5-volt connection. Opposite it is the ground connection, and the terminal in the middle is the V out, the voltage out. And what we'll do is we'll solder this in place, and then we'll run some wires to appropriately connect to the power jack. So let's begin soldering. Now what we're doing here is soldering the power jack in place. Notice how the soldering iron is placed against a part and then heats the part, and the solder is melted on the part. That's the proper way to solder. Many people don't know that and think that you put the solder on the iron and then the iron on the part. What we're doing here is cutting some heat shrink tubing in little short pieces. What is necessary is the transistor can that the sensor is mounted in is metal and needs to be isolated from the pads, so we cannot rest the can directly against the circuit board. We have to have a standoff. And you notice that the 3 terminals are insulated from the can. If we were to put that right against the circuit board, we'd have a problem because all the terminals would be shorted to each other. So this is a quick and dirty way to create a standoff. Next, I manipulated this in place. It's ready for being soldered. The 3 terminals, that is ground. That terminal is voltage out. And finally, this terminal is the 5-volt supply. So here's what the assembly is going to look like. We need to add jumper wires now to connect the parts together. Notice that the sensor stands off the PCB. So to begin with, what I've done here is bend the 5-volt and ground connections and made little loops out of them and stuck the ends in nearby holes. This will make it convenient to add jumpers. This is the first jumper wire. it's red, it's going to be the 5-volt connection. Notice that one end is stripped a little bit longer than the other end. And this wire is stranded 26 gauge. You don't need anything thicker than 26 gauge. So we have the 5-volt connection sticking out of the hole. That's common with the lead from the 5-volt connection. And here we have the other end sticking through a hole near the 5-volt pin on the jack. Notice it's stranded wire, and when I did this, the strands kind of frayed, and so what you see is me dressing that up a bit. I should have pre-tinned that wire. But that's done. We have 5 volts running from the jack to the sensor. Now this jumper is black and is going to be the ground, and notice that I am pre-tinning to prevent this stranded wires from coming apart. And this is how I have it mounted now. You can see that the long end is going to reach over to the power jack ground. I just soldered the ground to the sensor, and there is that longer piece being soldered to the ground on the power jack. We're not done yet because we need a pigtail to bring out the signals. So we need a ground and we need a V out wire. This is the V out wire. And it's being soldered similarly to the other leads. So V out is done. We just need to add V ground, or rather ground, and I am pre-tinning this end. That then goes into the board, or rather I pre-tinned it so that I made a loop, and that loop hooks on to that loop, the ground lead, and makes for a mechanical fixturing while I add solder to make it an electrical fixture. So we're almost done except for twisting the leads. And after twisting the leads, I add some heat shrink tubing on the leads to keep them twisted. That's what you see here. A couple pieces of heat shrink tubing. We're done except for tinning the stranded wire ends on the signal out pigtail. This keeps them from fraying and coming apart when you attach clips to them. So we're done, and that's what it looks like.